Alrighty, it is time for day 16 of Advent of Code 2019. Today I'm going to attempt once again to do the problem as it opens at midnight, which is in just over 90 seconds here. And I tried this, I think, 2 days ago on stream. It did not go too well. The past few days have not gone too well for me, so I do not have high hopes of this. But fingers crossed, something can go magically my way. Somehow the problem will work for me. I don't know. Hopefully something goes right. But real quick before we get into it, I'm going to try a different video editing strategy here, maybe, to try and highlight kind of what I did last video with doing kind of sped up sections while I'm actually coding, and then kind of when I'm finished talking it over a bit and kind of summarizing what I did, or right before I do it, summarizing what I'm about to do. That way there's a lot I can talk before and after, and then just code and not to worry about also talking while I'm coding, which kind of is really hard for me recently with these problems getting harder and harder. So I might not try it this time because I will be doing this live and really quickly, so I won't have time to talk at all. But at any rate, that's something I'm planning in the future. So 30 seconds here until the puzzle opens up. No idea what the problem is. I have my base code set up. I have a file ready to dump my input into. This is how I start all the days off. So yeah. 3, 2, 1. Let's do this. Interesting. Okay, so we do need an integer array. This array is going to be the FFT, I think is what it is. And we're going to set this equal to program. Okay, so we needed to make our FFT, which is all the input digits. So we need to go ahead and create a new integer array. This will be equal to program.length, because it's going to be the same length as this. And then I equals 0 while I is less than FFT.length, I plus plus. Go through them all. We do FFT, whoops, I is going to be equal to program dot, it's not program, it's just input. I don't know, it's called program because I'm using it, I had been using it for other, encode problems. We're gonna do char at I, and what we're gonna do is then offset. So what is the ASCII table again? Okay. ASCII table 0 is 48, so offset it by 48. There we go, so that'll build up our int array. Good. So now that we have all the integers, what we do is now we need, okay, so for int I equals 0 while I is less than FFT.length I plus plus. So we're going to go through this how many times? We're going to go through this that many times. So we have this base pattern. So that's the base pattern. We get the offset at 1. So start at 0. So it's actually starting at 1. So, and I'm going to say in times equals I plus 1 just because I need to hold this in my head. So that's the number of times we repeat. So it's I plus 1. So it's going to be through each. So every time we do this, we're going to go through it again to actually calculate the new values. So we're going to do an int array here. This is going to be new FFT. I'm going to change this to FFT.length. So I have to create a new int array here. And we're going to set new FFT at I is going to be equal to this big long thing. Oh, we do this 3 times? Is this 3 loops? Is this going to be 3 loops here? Because we have this one for all the phases. Oh, it's 100 phases. Okay, never mind. So we just want 100 faces. Never mind. So here's the new FFT. And we're going to set new FFT J. This is K. Equal to what we get from here. So this is going to be int val. So you only take this. Okay, so we just need to figure out this base bit here. Because what we'll do, so equal to val, is what we need to do is we need to do FFT K and multiply it by some value like 1. This will be calculated later. And then we're actually going to do then math dot absolute of this in case it's negative. And then we're going to divide by 10 to get just the ones digits. Yes, I know that's not right. And then that's result. And so then result is added. Oh, you just, okay, never mind. Result is that. So it's actually, this is actually val plus equals that. And then this is where we do the math absolute. And we get the ones digits here. Okay. So now this is where we just got to do the whole base bit thing. So the base bit is going to be controlled by J, because this is the depth we're in. So J, so if I just do int, call this base, so J, so we need an int repeat equals J. So we'll do, ooh, this actually might work really well. If repeat equals 0, we start a new J, do int index equals 0. Index equals 0, so we do repeat equals 0, repeat equals J, index plus plus, and then we do base of index. And then we have new FFT, and then after this is done, FFT gets set equal to new FFT. Okay, let's start with what their example is. Run this. No, don't run it all. I also do run the right day too. System out print line. I'll make this run once. Print line FFT or arrays. Arrays dot toString FFT. There. Now run the right day again. Run today. Index. Index equals index plus 1 with the base dot length. I forgot about that looping issue. There we go. 4. Oh, we got 4 correct, but we got 0, 0, 0. Okay. Well, that's good to know that 4 got the right answer. We got the right answer to the first line. So that means then this repeat probably didn't work. Yeah, so the base is just not starting correctly. This should give me the same answer, right? Oh, wait, did that work? 4 8226158. Oh my, that actually worked. Wait. Okay. So now if I do a second iteration, remove this bit. Okay. 34040438. Oh my god. Okay. Give me that. And then let's put our input back in. And what we need are, what are the first 8 digits in the final? Okay. Run. 364370. 36437072. Those aren't the first 8 digits? No! Let's test these. Oh, it loses it at higher numbers? That's unfortunate. Okay. Let's go back to this. Let's see after 4 what this shows. Oh, you know, I forgot to turn it to 100. Wait. I forgot to change it to 100. Oh, that was it. No. I just forgot to change it to 100. Wait, no. Give me this again. 767958888. Wait 4 seconds. Please be right. Oh, it didn't give me it? Hold on. 1, 2, 3, 4, 5, 6, 7, 8. It's an 8. 2, 3, 4, 5, 6, 7, 8. Oh, I got it. No, it was ring 402. Sad, I wasn't that high last time. I got it in 20 minutes. I was actually really happy with that. Dang. Okay, so we still run this like normal. And we get to the end here. And so we need the first 7. So int first 7 new integer array, 7 long. All right, take those in. So now we have our first 7. So actually, you know what? First 7 equals first 7 times 10, offset it, and then add that. Okay. So now this will give us our 7-digit number. And we can then output what? First 7, just to make sure. So there we go. So now we have our 7-digit offset here. So we got to do this. So we run this, and we need to do, I think what we can do is we can do int, can you actually? It's repeated 1,000 times. I don't think that's going to make a difference. So if you copy this and paste it 76795. Oops. Do we still see 76795? We don't. For skipping exponential digits, we only care about those, what, 7 columns in this? So we could shortcut that. And so we have our first 7. And what we can do is take this, do it again, but instead of going from 0 to there, we're just doing it on I equals first 7 and then plus 7. Oh wait, sorry, not there. Sorry, on there, first 7 plus 7. And then this still runs like normal on all of them. Obviously, though, we can't do FFT 10,000 times, though. That's the only issue, is that it'd be 10,000 times. I didn't want to know how many. That's a lot of characters. 6 million? I can try it. So we're gonna do int FFT copy equals FFT.clone. And then we're gonna get to here, we're gonna do FFT. Is there something I can use in arrays? Arrays dots. Equals new int array, and we're gonna do FFT copy dot length times 10,000. We're gonna do a for loops of 4. I is less than FFT. I don't know how to like fill this 100,000 times. I can just do a list of integer. I can do it this way. This might be really still too slow. I don't know. Okay, and then we're gonna do list dot add all of FFT copy. Oh, it needs to be an integer. These apparently all need to be integers. Just so it can be happy. Okay. So do that, and then we can do FFT equals list dot toArray new integer 0. And in theory, this would do it. This is integer. In theory, this would get us it, but I don't know how slowly. And then what we would need to do is then offset by that much. So we have to do a system out print line of FFT. Can I do arrays dot copy of range FFT arrays dot toString copy of range, and we would be doing this as our range. 2 plus 7. Inclusive, exclusive. Exclusive, okay. YOLO. Null pointer. FFT of K is a null. Oh. Oh, we still need to go through all of them, though. I gotcha. New FFT, right. It's going to be all of them, but we're still skipping all of these J's. What if actually, no. What I should do is I should just do FFT.clone. Oh, no way. No way did I get an answer. That's not 8, 1. Is that 7 digits? Oh, no, it's only 7 digits because I did 7, not 8. Oops. Run it again. Remove these excess outputs. Just give it a second. Give it a second to calculate. I doubt this is right. I will be amazed if this is right. Nope.
At night was born to find mythical, so mystical, think what you like. You could be the sword, the shield, defender of the people down below. You know I fought for love. You know I fought for love. You know I fought for love. Be kind to those around you, don't be merciless. Remember me, for my name is Perseus. My name is Perseus. My name is Perseus. My name is Perseus.
That is really slow, but 7, 8, that's right. I don't have high hopes for mine being fast enough, though. I'll give it some time, but I don't have high hopes. In the meantime, can I make this any faster? So you need to go for the full length. So because of the mapping here, I'll pull this over while we wait. So because of the mapping here, this is what their like little graph looks like for like adding things up I've been looking at. So because if we just want this 4th line here, this 4th line doesn't care about the first 3 inputs. So we don't need to do math with those at all. Like none of these phases we do need to do math with the first 3. So we can just ignore them completely. However, we do need the last few bit. And that's kind of, whatever though. But trying to figure out more, and then obviously I skipped. I guess it was double doing it, but I've also skipped because there's a horizontal line here. Any other like cuts I can make to make this better? Because it's obviously striping, but I can't think of any other way to go about this. It's not. I don't think it's insanely slow. I mean, it's slow, but I don't think it's end of the universe slow. We can do is do long. I could calculate this, so time. Oops. And then output system dot. I could calculate this, let it run, and see how long it takes to get the very first one, and then we'd multiply by 100. So actually, technically, I should know. I think I was on the right path. Oh, took that long. Calculator times 100 divided by 1,000 milliseconds in a second, divided by 60 seconds in a minute, divided by 67 in 24 hours a day. It only takes 6 days. So yeah, it took 88 seconds, needs to do 100 of them. 60 minutes. Wait. That seconds. Oh, no. It would take 2.4 hours. Sorry. It would take 2.4 hours. So yeah, and this would get it, and just it works. It's there. It would get it, but I think I'm on the right path here of this whole shifting bit. It's faster. It's actually about half the time it takes. So it's that many. So we run it 100 times 1,000 milliseconds divided by 60 seconds. This will take an hour. So we've had the time. It'll only take an hour. Yeah, in theory, this one will only take an hour this time, but there's gotta be some better way, but I don't know any better way. I guess I'll let this run for an hour, and I get an answer, and yeah. Oh, I got it. Okay. That's right. Okay, never mind. I was literally about to end when I thought of a better shortcut. There we go. Part 2 done. Okay, so the shortcut that I ended up using there was that I didn't need that whole second for loop. So basically, because let me get the calendar thing back here. So because there's a little trick in here that it's hard to see on this. Yeah, that works well enough. So there's a little trick here, so you can see is at the end here, the 4 always ends. It's always the last number is a 4. You'll notice that this number is the sum of these mod 10. This is the sum of these mod 10. This is the sum of these mod 10. So you'll notice that what I was doing was I was saying, starting here, I was summing all of these up mod 10, going here, summing all of these up mod 10, starting here, summing all of these up mod 10. And then I just realized wait, if we're just always summing these up, why not start here, sum this up, mod 10. Well, actually, this one doesn't matter. Count the first, actually, yeah, sorry. Sum this up, mod 10, put it down here. Sum these up, mod 10, put it here. Sum these up, mod 10 here. That way we can keep a running total. So we've 4, 6, mod 10, 0. 10 plus 6 is 16, mod 10 is 6. 16 plus 4 is 20, mod 10 is 0. So where I'm just summing up backwards, and every time I go through backwards, I am then using that to put the new value in here. Much, much, much more efficient. It just took me a second to figure that out. Okay, so to summarize up today, basically we read in our input as normal. We broke up the input into the individual digits, as you can see here. And from there, we grabbed the first 7. That's used for part 2. We hold on to those, make a copy of it for part 2 as well. We go through all of them, and what we do is we apply a pattern here. So this base pattern, we apply that pattern to all the digits, add them all up, and keep doing phases, basically what the problem says. We go through our input here, we apply this a phase pattern algorithm, or what math operation, whatever you want to call it, to them. We do that, we convert it, and then for part 2 here, we go through, we start at the last 7 digits that we want. So for part 2, we are given this bit is where we want the offset to be for our actual message. We go through 100 times, we only read those bits or those digits on in the string, and we count backwards because there is a pattern. Like I said, I just explained the pattern a second ago. Part 2 really relied upon you noticing that pattern and that trick. Honestly, without it, I mean, I had it quick. It just wasn't fast enough. And then I got the pattern, which makes it really fast. So yeah, so hopefully the editing of this video goes well. But on that note, I will see you guys all tomorrow for day 17, because it's 16 now. So see you guys then. Peace out.